So if you can stand a little bit closer to that one foot right there, introduce yourself. We're ready to rock and roll.
Should I stay here the whole time?
You can walk back and forth, just
That's kind of great designs, probably.
he doesn't have to stand in front of Vector.
Right, just right there.
You're good right there.
Okay, puts me on. So, good evening, everybody. My name is Rob Laneve from Air Control Products, and thank you for being here tonight. And Tom and I had communicated a few weeks ago about coming in to talk about makeup air ventilation. So, you're probably familiar with the concept or the idea of makeup air. So Tom and I went over kind of an agenda of things that maybe to cover just to refresh your memory or to maybe introduce you to something new. So at Air Control Products, we're manufacturers representatives and we represent 30 or 40 different manufacturers. We kind of have two groups, and a third group would be our architectural division, but on the HVAC side, we have a group that calls on contractors, and that's our sales staff, and we have an engineering team that calls on contractors, consulting engineers, architects, whoever would be involved with the application of our products, the selection application. I say predominantly we're calling on the engineers who are designing the facilities, but we're many times with our sales staff, with the contractors helping to talk about our products and how they're being utilized, or maybe a startup application or troubleshooting things of that nature. So thank you for that. Course objectives, I'm going to show a list of things, but is there anything that you would like to bring forth that you say, hey, Rob, be sure we try to cover this, that maybe I can enlighten? So if there's nothing particular, we'll just continue on.
Brian would like to know about DOAS.
Okay, DOAS, we can put that on.
I was just gonna say that.
Okay, Brian was going to say that. May I use your board?
Certainly.
Put DOAS units. If anything else comes up along the way, we can add it. But in terms of the course itself, fan selection. So we have this makeup air unit. We want to talk about the type of fan that would go into the unit, what we're finding the industry is using, what's most efficient, things of that nature. Next, we'll talk about heating technologies, might be direct gas heating, indirect gas heating, steam coils, things of that nature. Then we'll talk about cooling, package DX, split DX, chilled water. Lastly, controls, kind of what brings everything together. Now that we have this unit all assembled, what's going to make it all operate. And we're just going to go from one topic to another. So along the way, if we need to stop and dive deeper, we can. In terms of makeup air, equipment that's providing conditioned outdoor air to replace exhausted air. Okay, so typically from a process as opposed to air that we're heating and cooling. So makeup is to replace what's being taken out. So one might be a kitchen application. We have a hood that's being taking out the effluent from the cooking appliances. We need to replace that air with makeup air. Might be industrial application where we have snorkels on a welding process, exhausting air out of the building. We need to bring in makeup air for that air. Might be a warehouse. We're trying to ventilate the warehouse, maybe taking out other contaminants or just bringing fresh air through the building. Warehouse. In terms of functions of the makeup air, we want to replace the air from local general exhaust, which I just mentioned. We want to control infiltration with positive pressure. So if a building ever became too negative, you'd be pulling in contaminants from the outside, maybe pulling in just cold air, dust, dirt, things of that nature. So a building always want to maintain slightly positive to keep that.
If you don't keep it slightly positive, all the engineering goes out the window.
Exactly. Confine contaminants and reduce their concentration. So if we did have a buildup of contaminants, whether it be CO2 from people or something else, we can bring in fresh air. We're diluting that contaminant. Sometimes people say the solution to pollution is dilution. Solution is diffusion. Okay. Control building temperature and humidity levels. Pretty self-explanatory, but you have a condition where a building needs heat, that outside air can help provide that. In terms of problems with insufficient makeup air, we could have a condition of draft complaint. So if we begin to go negative, we're just pulling air in through under a door or cracking a window. Maybe that's annoying to somebody because we're getting, most of the times I reference cold because people recognize that. So it's 0 degrees, you pull this air in, that's not good. Natural draft stacks become ineffective. If you do have a gravity or natural stack and you start going negative, you could be pulling those products of combustion down into the space and be in bad condition. The last one I think I've all encountered somewhere, doors difficult to open, and it doesn't take a lot of pressure to create that. So mostly I see this on restaurants. And for whatever reason, maybe like Chinese restaurants, I think they shut their air, make up air up all the time. You try to open that door, they're doing heavy duty cooking. They have fair amount.
Make up here.
So a short, quick calculation. So it's about 12 pounds or just having a 0.1 inches of water column difference that you're having to try to pull on that door. And that's just a 7 foot by 3 foot door. The door could be bigger and the pressure could be more, but it's kind of like, you know, it takes some effort to do that. 12 pounds. In terms of fans themselves, forward curve fans is the top one. You see that's a belt drive arrangement. Forward curved wheel, air coming in the backside, coming out. We're pressurizing this this housing itself. Backward curved plenum fan. This particular fan, the air is coming in the end and it's coming out 90 degrees from the wheel. And this will be encased in a enclosure or the housing. It hit the housing and then continue down its way. And the last one, mixed flow plenum fan. So plenum, but the difference here is the mixed flow, instead of the air coming in and coming out at 90 degrees, it's coming out at 45 degrees. And it has a different sound profile, but it's more efficient. And I have a graph that will show you the efficiency gains just by using a mixed flow plenum. And then direct drive arrangement. More and more we see direct drive arrangements simply because we eliminate the maintenance of the belts, misalignment, the loss of efficiency, things of that nature. Sort of covered this a little bit already, but remembering you're pressurizing the fan housing. In this particular case with that forward curve, this air, this area is neutral. The air is coming in here, being pushed down, or it's coming, I guess, through the unit. It's
Telling too long.
oh, I still have it on my computer, so it's still up there.
Yes,
I just thought it was a cable.
The one time I actually talked.
It's your fault.
Not
your fault. I'm just
gonna
I can continue on and if we think about that mixed flow wheel, again, it's pressurizing that plenum or that box and then continuing on. Now, the advantage to that is we can have that air come out the end, the sides, the top or bottom. And many times in the field, it's configurable that we can change a panel location. For some reason, there's a change and says, oh, shoot, we want to end this trip. Now we want side this trip. We can take those panels off and adjust. And that forward curve housing, it's either coming out the end or we can rotate the housing up or down, but you can't go side left or right. Oh, go back. There we go. Thank you, Tom.
Sorry about that.
No worries. So I described the mixed flow plenum and then the forward curve. So key differences against those directions, I just mentioned those. I don't think I missed anything there. Blank off, field conversion. So this is a comparison or breakdown of those three arrangements. And we sort of had some pros and cons that we'll go through. So in terms of pros, direct drive eliminated the maintenance in the belts. Volume wise, it might have a little greater volume there than the other two, but we lose a little bit of static pressure capability. So highest static is in the backward curve. Mixed flow still up to 3 inches, but now you get into energy and peak total efficiency. You see where these greatly outweigh the forward curve. So more and more movement towards these backward curve or mixed flow wheels. And then in terms of dollars, you're not paying that much more, almost similar cost to this arrangement. If you get into this wheel is a little harder to make, so it does cost a little bit more. In terms of the cons, we talked about having maintenance of belts, lower efficiency, and then a little more dollars.
Rob, how much in the business, how much of your sales is based on efficiency? I mean, when somebody comes to you and say, I want the most efficient unit, or is it somebody say, I just want a unit that works well?
Okay, two answers to that. First, how many times somebody, hey, Rob, I want the most efficient? Not very often. Second answer, how much of it relies upon us? we take it upon ourselves to look at efficiency and say, this is the more efficient fan. It costs 10% more, whatever that is. Lifetime of the unit. We try to look in the total life cycle of that unit to that building, to that owner, whoever's using it. Life cycle
About
cost.
60, 70 years,
Pardon me?
60, 70 years,
We like to think 100 years, but reality is
20.
10, 15, 20 years. So like there's certain ASHRAE charts that'll publish like expected lifespan of equipment. And so I think they list like rooftop units, 10, 12, 15 years, maybe it's 20, but we think it's, we kind of keep that mindset, try to get the most efficient. Now, sometimes like in our software caps, you'll get 7 or 8 selections and you might get 10 or 20% more efficient, but it's 3 times the cost or something that's probably not going to fly. So we kind of moderate that, keep track of that. In terms of the wheels and the performance, I just want to touch on this briefly because of that mixed flow and manage. So in an axial fan, you tend to get higher volume and lower static capability. That air is coming in parallel to the shaft and exiting parallel to the shaft. That's the nature of an axial wheel. When you get to a centrifugal wheel, the air is coming in parallel to the shaft but exiting perpendicular. And the same thing happens with the mixed flow, but it comes out at 45. So a centrifugal has higher pressure capability and maybe a little less CFM versus that axial. And the mixed flow is kind of right in the middle. Hence, it's a mixture between the centrifugal and the axial. And it sounds different too. So sometimes an axial will be like a little more whiny, a centrifugal is a little more rumbly, but a mixed flow is kind of like right in the middle. So it's a little easier on the ear. This is going to go through a comparison of a forward curve at 1100 RPM, a mixed flow at 1222. And then we're going to show a difference in brake horsepower and how much is gained by just going to that mixed flow. So anything time we're going to have less brake horsepower, we're going to have energy savings. If we pick a point along here and about 12,000 CFM at 1 inch of static, we can show that the mixed flow has a 55% savings in brake horsepower. And that can be huge for an owner that's operating and continually has makeup air. So they have this process that maybe operates 8, 10, 12, 20 hours a day, depending on their shifts. This is savings every time it's operating, going to that mixed flow.
Can the unit be upgraded? So if you have a belt drive system to begin with, and you someone says, hey, I don't want to replace the unit, but I want to be more efficient, green piece, blah, blah, blah. Can it be upgraded to that?
It would take a little bit of investigation. I won't say no, it just hasn't happened very often. So if we go back to the housing arrangement, if I get there quick, which one here? Or
Switch to a drive, knock it down. It's the quickest way. It doesn't have.
So like this,
So, well, I'm just,
in terms of mounting, so this, if you look at this base plate, that this arrangement, if we can pull that out and we replace it with this base that support it,
Yeah.
it seems feasible. Do
all
we have
it is basically a draft inducer, more or less.
this one here?
So,
Is it okay?
I mean, you're just throwing air.
Yeah, right. So if these were the same dimensions and everything was aligned, I would say yes, but do we have that very often? No. So
It was crawl inside the squirrel cage,
What's that?
lay down in there.
Is there a significant difference in upfront cost between the forward curve and the mixed flow? Is it like,
no, those two are pretty similar.
Okay.
It's just when you get to that other centrifugal with. Okay, so we covered that. And if I'm in your way. No, you're fine, you're fine.
you can't see it?
There is that.
So, if I mention the words overloading versus non-overloading, have you heard that before in terms of fan wheels? A little bit, maybe no, okay. So, we're gonna look at a comparison of a mixed flow wheel and a forward curve wheel. This is the RPM line, and it can be arbitrary, but of the mixed flow and the forward curve. So this is, when we think back to that previous slide, if this was 1100 RPM and this was 1200. It doesn't really matter the value. The system curve defines the CFM and the static pressure we're operating against. So this is a system that's installed, and let's say that system was requiring 12,000 CFM, and it was against 1.5 inches of static pressure. that intersection of the RPM and the system is your operating point. These dashed lines are the brake horsepower curves of the motor, of the system, of the fan system. So if we pick a point on there and say, okay, that's our operating point, and we want to read to our brake horsepower, we read up to these curves. So the system curve read up to the mixed flow wheel as an brake horsepower, and we'll call it 5.5 for our discussion purposes. The forward curve wheel has a brake horsepower closer to, let's say, 7.75 for round numbers, let's just call it that. What happens in an overloading wheel is that if there's a reduction in system pressure for whatever reason, the system may be changed or maybe it wasn't installed the way it was drawn, it was just installed better. So we said, okay, we have less system pressure, and to move this amount of air, we're going to stay on the same RPM curve, but we don't need as much pressure to move 12,000 CFM. And that curve ends up coming down here, and you end up coming up through here. Okay, you imagine this being parallel coming up through here. So we're going to pick a point out here. What happens to the brake horsepower on the forward curve wheel?
It goes up even.
It goes up even higher. You get to a condition where you could overload the motor that you have.
Depending on the horsepower you select.
You got it, exactly. But what happens to the mixed flow point? It actually comes down slightly. So normally when you're selecting these mixed flow wheels, you're near their peak efficiency, peak brake horsepower. And if that condition happens, you're still safe, but it happens on a forward curve wheel, that could be overloaded.
Such as somebody's running it with the door open on the side of the unit, so you can select a lot lower horsepower motor,
Exactly.
which saves you on your initial cost as well as efficiency.
You got it. You got it. You know the story. Another sidebar to this, like terminal units, we have a statement that says do not operate terminal unit without discharge ductwork. Most terminal units have little forward curve wheels. They start operating without ductwork, they overload it, they burn it out, be like, oh, I was just using it to circulate air or something. Be like, yeah, best not to do that. Connects at least something to it.
But if you've got a drive, you can program all your overloads in the drive usually too.
Mhm. Yeah,
Save it.
and this particular stuff, our units come like standard with VFDs and drives because they're direct drive. On the little terminal box, it's just a little rheostat controller. So we went through this already in terms of the operating points. And if we step back and look at a selection and begin to watch those operating power and the sound levels of this different arrangements. So in the forward curve, 7.26, this is 10,000 CFM. 10,000 CFM at 0.5 inches, 726, 79 dBA. This is our operating curve. If we look to the backward curved fan, you'll see less operating power, slightly louder sound just because of the nature of that wheel. And then you get to that mixed flow, lower operating power, the lowest of the three, and a sound very similar to the forward curve, but quieter. So you see a difference of about 5. Difference of 3, not everybody can perceive, only really good ears. Over time, our ears get worse, we hear less differences. Difference of 5, most people can recognize. And the difference of 10 is twice. So a difference of 10 would be twice as loud or half as loud, depending which way you're going. So this one, if we look at this again, this was at 79, this was at 74. So you would notice that difference if you install those 2 units. If you installed, back this way to this backward curve, you definitely would notice the difference of this versus the other one. One more time, 79 to 82, a difference of 3. You may or may not notice, some people can notice the octave bands differently or the tone, it just depends. But know that mixed flow has definitely sound advantages too. In terms of kind of finished with fans, any questions on those? Kind of rifle through those because we want to get into the makeup area, but okay. In terms of heating technologies, direct gas, indirect gas. Direct gas, that flame is going to be right in the airstream. This is a flame picture of a manifold. The gas comes in, fires, comes off the baffles and then drawn into the air. Indirect fire, you're familiar with that, heat exchanger firing down a series of tubes, could be a serpentine tube or clamshell. And then electric, we have open coil, which is the resistance wire, and then this attempts to show a picture of a thin tubular element where the heating element's in a tube that has fins on it. So maybe you had an area that you were concerned about moisture, contaminant, you didn't want it to catch on those open wires, so you go with a thin tubular element. And then lastly, steam and hot water coils, which are pretty self-explanatory. So burner mounted directly in the supply airstream, the byproducts of combustion carry directly to the space. It's diluted to safe levels with that outside air that's coming over it, but it needs to, people need to understand this is going right into the building. Just the nature of what it is, but the volume is such that it's not, doesn't build up contaminants, and it's 92% efficient. So that is very,
Why not 100?
you lose 8% to the water vapor combustion. So out of there comes CO2, water vapor, and it just, it's not 100%. In terms of testing information, OSHA is going to develop 8-hour limits. ANSI standards govern non-circulating direct gas and recirculating direct gas. You never want to, and it is part of the code, you can never recirculate air over the burner. You can only pass once. So if you have a variable volume burner, there's always going to be like a bypass around the burner. And we have another picture of that to show that. So in terms of levels of combustion products, carbon monoxide, 5 parts per million, aliphatic aldehydes, 1 part, and nitrogen dioxide, 0.5. So that's when the burner's tested and you receive your ETL listing by the manufacturer, that's what they're testing against, if the proper combustion is occurring at that direct gas fire burner. ETL ensures compliance with those standards. So that's a close-up in terms of the manifold itself. Stainless steel mix I mentioned a little bit earlier, the flame rod or UV detection to make sure that everything's firing correctly, the spark igniter, and then the manifold at the bottom where the gas is going to come in and begin burning or begin combustion. Cast aluminum manifold is important versus a cast iron. Manufacturers choose these one way or the other. The challenge with the cast iron is that over time, the little orifices will begin to rust and they'll plug. And so now you begin to lose firing capacity because of the rust in the holes. So then you have to go in and clean those out or replace the burner. The burner is made in different modules or different sections. You can see them bolted together. Each one usually is about 400 MVH. So if we had 1600. Each section I think is like maybe, I don't know if it's a foot or 8 inches. It's about, if I remember right, it's about that big. So maybe it's a foot. But we would assemble them appropriately to achieve that MVH required, depending on the air volume and the required heating capacity.
Says aluminum can handle LAT.
Leaving air temperature of 800.
Oh, leaving air.
Okay.
The manifold doesn't see that, the manifold sees energy there.
Yes. So, well, yes, this is gonna, the gas come in the flame here. So if this whole assembly, I don't know if we go back. Maybe the next
Whose burners are you using?
sheet.
Sorry.
Is it Midco?
Midco.
I think that I've heard that name before.
Midco, Maxon.
Maxon, I've heard Maxon before. So Green Neck, I think they have a certain standard of what they're buying, and I think they're aggressive in their pricing. Where if somebody,
And I think Engineered Air makes their own. That looks like the pilot that engineered, but I think that's a Midco pilot.
okay, yeah. So I apologize not knowing specifically, but I have heard those names before. But their key is they always will use an aluminum manifold. Green Neck is standardized, and others may have also. In terms of operation, a burner requires proper air velocity to achieve that air to fuel mixture. So when it's set up, you're going to measure a differential pressure across the burner, and we're going to adjust a profile to maintain that velocity across the burner. This is key to draw that flame off, and you have complete combustion. We don't want to have a condition where you have incomplete combustion and develop carbon monoxide. there's gonna be baffle plates, and we have instructions of how to set that up, but it's the idea of velocity and the pressure across the burner. In terms of variable volume, I mentioned earlier, so this is called a bypass damper, and for Green Neck it's self-adjusting. So as we bring in more outside air, it's gonna allow it to drive over the burner. But as we bring in less or variable volume condition, back that off, this is gonna close and drive off more air over the burner so that we maintain that velocity. So we can't get to a
So
condition.
it's a combination of the automatically adjusting bypass damper and the fixed
Yes,
profile dampers.
you got it. Yeah.
Dialed in.
Air velocity over the burner remain constant. VV is accounted for by the bypass. Mentioned that variable frequency earlier. We have that one, and then the pressure drops held constant. This is tempting to show that you could vary the burner, but the performance of the air is going to be a function of the pressure drop over the burner, but also the fan. So if you look at a fan curve, there's always a line that you do not select to the left of. Some people will call it like the surge line or the do not operate line. So if there's a time where if this was shifted for whatever reason, and we say, well, look, we're going from our operating point, and let's say the line was over here, we say, hey, we can't go below 6,000 CFM because we're crossing the line. In this particular case, the line allows us to go to 16,000. So we could go from this point, call it 46,000 down to 16,000. That's pretty good in terms of variable volume. Most times I'm talking with engineers about like a 50% turn down. They usually come out 50%. They won't have much need for that more than that. But you could, and one the other day, they wanted to get to like 35%, and we could still do it. The fan curve allowed that. So
You're talking about airflow now,
airflow.
not the burner.
I know the burner will be adjusted self, and I think the next slide talks about, just mentioned that 30-1. Okay, so it's
On
usually
the direct fire,
correct on the direct fire.
the indirect fire, you don't get that.
Not 30-1, but we can get to 16-1. 4-1 is usually a start, and then you can, depending on the assembly, sometimes I see 10-1, but if we have 3 burners, we can get 2, sometimes you get 1 to 8-1, and then you get 2 burners, get you 16-1, 3 burners at 4, 12 to
So
1.
just one burner, the best you can do was how much?
I've seen it anywhere from 4 to 8 to 12.
That's fine.
Okay. 30-1 turn down, low fire set point is critical. We're looking at 15-1. So in terms of this may be capable, but many times we're not seeing that need for that, but we do want to review it when appropriate. And then electronic modulation. So to control the temperature. Most of the time we see discharge control. So you're going to have a temperature sensor mounted at the factory to maintain a set point. And maybe it's 70 degrees for space neutral. Maybe it's 95 with more heating. But that discharge sensor is controlling what that burner needs to fire at to create that leading air. In terms of discharge control through override, let's say you're set at 70 and over on the wall you have a thermostat and you have it set at 65. And it says, well, okay, I'm below 65. I want to be to 65. What it does, it bumps the leaving air temperature to maybe,
Resets it,
yeah, you got it.
depending on how far you're offset.
You got it. And then it brings it back once you're satisfied. So that's called override. Room control. I don't see that very much on makeup air because we're more concerned about the air than we are the space, because you're just replacing the air that's being exhausted. You have other means of heating space. And then external signal, if somebody does want to run the unit through an automation system or some other external, we allow them to do that. In terms of indirect gas, any questions on direct? Seems like everybody's familiar with that. Indirect gas, heat exchangers to transfer that energy. So here the flame is coming down the tube and then out the collection box, little power exhauster pulling that contaminants through the tubes and then exhausting it outside. Very common for rooftop units. What you see here is a tubular arrangement, the clamshell you're familiar with, and then the drum and tube. I don't see too many of those. And everything we do from Green Neck is the tubular arrangement, 80% efficient. So some people say, well, wait a minute, I have my furnace at home does 92% and it has a heat exchanger, why don't you get to 92%? Or something, figure of that nature. So to do that, we looked at an example, and what it comes down to is kind of, let's say, return on the investment or lack thereof. So if we get to a 92%, usually what does that require after the primary heat exchanger? A secondary heat exchanger, higher condensing. So you have two challenges. One, the condensing flue gases, what are you gonna do with those? Now you also pay for this pressure drop on the double heat exchanger and secondary heat exchanger. Your operating power is gonna go up, electrical usage goes up, and a little less gas usage, but it's kind of offset in a negative way by power consumption, and actually costs you a few more dollars to gain to 92%. So for what we're doing in terms of 6,000 CFM as an example, in Cleveland, Ohio, for 70 degrees, doesn't make a lot of sense. So some manufacturers have gone down this road, many have chosen not to, just because of the nature of the beast that we just bring in outside here.
Sounds like the condensing part would be a big problem.
Yeah,
Yeah, and then what do? You can't run it in PVC drains or steel
Heat
drains.
tape and all that other stuff.
Let it run out the rubber roof.
Prime example of a carbureted car versus a Tesla. Get just as
Do
good.
you have all electric makeup air units in there?
we can. So in terms of what that will be coming up after indirect, we talked about modulation, 4-to-1 standards, some we can go up higher, as high up to 16-to-1. And the controllers, basically the brains of the unit is what's going to drive this. We prefer to control the modulation. We Green Neck purchases, I think it's Maxtrol and some other modulating burner controls. We let somebody else do it, then they really have to know the sequencing and stuff. It's not impossible, but we kind of like to keep that within the controller that we can provide and program. Similar control strategies to the direct gas. When does turn down matter? When the high temperature rise application. So where makeup air, if you did switch the idea of makeup air to be more occupant driven as opposed to just replacing air, you want to watch that turn down. We don't want a condition where you overshoot and then it can't turn down and then it shuts off. It gets cold, then it overshoots and it comes down. And I have a graph that kind of shows that in a minute, but it's just when we get to 4-to-1, that's kind of the trouble when you're trying to maintain comfort because they overshoot. And I think this graph shows it
And
well.
people all call it a heater.
Pardon me?
People call it a heater.
Yeah,
They don't realize it's making air.
you got it. So 4-to-1 modulation, high fire. So about 50 seconds, it's going to high fire, then it's going to go down to low, and then it's going to say, okay, we're satisfied if this was what we're trying to get to in terms of the required temperature rise. Here it's a low temperature rise, but we have a high 15-degree minimum temperature rise. So you see what happens, and people tend to feel warm, cold, and it's not always pleasant. So if we go to a 16-to-1 modulating, now you're talking about something that can go 3.75 degree rise in terms of that pressure versus 15. So at 3.7, we're trying to maintain a 5-degree temperature rise. We can come down in that same 50 seconds and then just modulates along here. So you don't have that big swing. So there are times when the modulation becomes a big deal. Okay, we talked about the burners. This is how it'd be arranged in the unit. This is where I talk about outside air coming in, being filtered across the burner into the airstream. This is an example of a 3-way discharge you might have in a warehouse, just dispersing the air. And then the indirect gas, same thing across the, looks like this one might have additional coils, condenser, some probably hot gas reheat, DX coil, and then across the heating section into the space.
I have a question.
Yes.
How do we deal with the filters when, like in this region here where we have blizzards and it snows and the next day it's sunny out and it's fine? I mean, how do you deal with that snow? I mean, you're pulling in 12,000 CFM from outdoors. What eliminates the snow? Or
So I'm a little more conservative, and what I like to see is I will add another filter section here that on this, well, the filtering section I use is the weather hood I'll use with metal mesh filters to try to catch some of that stuff. I never want to see just an expanded metal screen here and media filters here, because these will become saturated pretty quick. They'll be wet and then be sucked in and a bad thing. So I like to see a metal mesh filter in the weather hood. You have the option of like bird screen or metal mesh. And then a filter section here with maybe MERV 8 or 13, or somebody really wants.
So even then, I've seen actual 1 inch mesh when it's super cold outside, like in the single digits or negatives, will frost over to where you gotta go kick it and knock the ice off, it just restore airflow.
That's just the nature of the beast. I mean,
Yeah.
90% furnaces right out here suck in through the intakes.
But I mean, we have a recent bout this year where the entire units is packed with snow drift, and that
Yeah.
one kind of dead in the water.
I don't know if I have a great answer to that, outside of, heat tracing. Yeah.
I'm talking about one time, maybe like a
There's your money.
intermittent use, infrared, like an infrared heater or something like that mounted in the filter compartment.
Interesting. Yeah. There is
I
some,
just wonder if anybody made anything like that.
there is a product, I think it's called, Snow Stop SNO dash TR or STOP, I think it is. That's just, I don't think the W's in there, but Snow Stop. And what they did is they took a metal mesh filter and they embedded a heating wire in it. And somehow you wire this up and
Into
it
that
melts.
NiCad, nichrome wire. What I do?
big toaster.
Yeah, basically,
Right.
yeah, that's
Put my lunch in.
yeah. But that was one thing I've seen. In terms of comparison, we kind of went through this already, the pros of each modulation or efficiency. And I talked about the capacity of each section. That's kind of a reference. Winds used in direct gas heating. So there's a NFPA 54 does not allow you to use a direct gas-fired appliance where there's sleeping quarters. Okay, the concern is you're putting those products of combustion into a space, somebody stays in there over time, maybe you have a malfunction, now carbon monoxide, and you have a fatality. So anytime there's sleeping quarters, we won't use it. That's many times I question the engineer. What's the application? Where you're using this? They talk about sleeping. I said, oh, can't use direct gas fire. So that takes it off. So we go into that. So general rule, direct gas when ventilating for a process, indirect gas when ventilating for occupants. And then the CO2 would be another component where you could have a buildup of CO2. In addition, if you have malfunction, you could have the CO, but it's just normal combustion, you'll have the CO2 in the water vapor, and you could have a buildup of this. And anytime you're trying to ventilate to avoid a buildup of CO2.
Direct gas, it's all in.
So, and this kind of reiterates the fact that direct gas is to replace air exhausting from a process or for general ventilation. Indirect gas ventilating for occupancy. In terms of electric heat, it is 100% efficient. The energy you put into that coil is going to come out, but there's a reference to, don't forget, we are generating that power or that electricity probably inefficient back at the plant. So it's not like
By the time it comes out your outlet, it's less than 20%.
right, for the line losses and everything else. So, there's the buzzword now, electrification, decarbonization, and this idea of moving to all electric buildings. I think New York has implemented a thing, so you shall not have any more gas-fired appliances installed new. California, so I don't know where we'll meet when it all shakes out, but there's concerns like, okay, if we all go electric,
You're already doing that? Investing in copper.
and in fact that can the grid support such a system, and we have to go to renewables. So we'll see where it ends up, but be aware that it is out there. In terms of control, we talked about modulating gas a few minutes ago. This is going to modulate most of the times through SCR, so silicone control rectifiers and infinite turn down. Essentially, it works on a cycle. If we look at the 60 cycles per second, it looks at 2-second increments. So you get 120 points of control, and it just pulse width modulates the power on and off. So if you wanted 50%, it's going to be on 50%, off 50%, but it happens at a rapid rate that you're not going to sense that by both units off.
Just like a VFD.
Open coil, this is fin tubular, I mentioned that, and then what we do watch is sometimes somebody says, well, I have this large amount of outside air, if we go electric, now that load on the electrical panel, wiring gets pretty big, and they're like, oh, shoot, I didn't realize it was gonna be a, X amps.
So then they don't want it to, but then they tell you they want it to be, they want cooling. Well, you're back, you must be with the electric heat, because you're gonna need it for the cooling.
Excuse me, when it comes to the compressors, right? So, steam or hot water, pretty self-explanatory. We're gonna have a boiler, you generate steam or hot water, the efficiency kind of governs it. We always want to watch hot water coils freezing. We're gonna bring this outside air in, maybe, it's not flowing. Now you have this fluid, so you want to have glycol there to prevent coil freezing and have a problem with that. We do use steam distributing coils, so that's a tube within a tube when we go to steam coils rather than just a single tube, and that helps to prevent some freezing. But there are no guarantees against that. That we say if you're going to go this route, you got to have provisions in place like shut down the unit if you have no heat and the temperature is below, like 45. I don't. Obviously, it's not going to freeze at 45, but it's like give yourself some safety factor. Don't wait till it gets to like, hey, it's 5. Let's shut the unit off.
Too late.
Yeah. In terms of package or cooling technologies, package DX, split DX, chilled water, and evaporative cooling. I don't see evaporative cooling very often in our area. That's usually the drier climates out west. You pick in Arizona or
Arizona.
yeah, basically. Over the chilled water, you got to have that chiller. And maybe you already have it, so then you can use it. If split DX, you heat the unit inside, but you can't reject the heat inside, so now you have a remote condenser, or the package DX is I would say what we see most often when somebody wants cooling. In the package DX, obviously it's fully integrated, you're familiar with that. The final charge and startup, it comes to a unit with a pre-charge, but we don't fill it all the way. So there is a comment saying you got to start this unit up. You got to verify the charge. You might have to prime it or add a little more to it to get to where we need to be. Standard scrolls, I don't see those used very often anymore. As far as on or off, digital scrolls were pretty popular for a while, but that was a case where the scrolls unloading and loading for capacity control, and you hear that click, click, clicking sound, which I've heard it once, and it can, I don't know, you guys have probably all heard it in the field, but it can be annoying if you're not familiar with it. Like, what is going on? And it's like, it's just that compressor unloading and reloading. But the more efficient way to do it is that inverter scroll. So we're putting VFDs on the compressors, and we're actually varying the speed. So now as you drop that speed down, you're saving energy. In the digital, it's running full time, all the time, 100%. It's just loading, unloading. So you're not really saving in terms of operating that compressor. So more inverter scroll than digital scroll.
Staging and inversion. You can only go down to a minimum amount, right? Oil pressure.
And when you have two compressors, the second will be full speed and this will be modulated. Because if you're going to bring this up to full speed, this one needs to run at full speed. You don't need two modulating compressors. So you're going to run both full speed and then modulate this one down. If your capacity was, 50, or let's say it was, how would I do this? 100% here. If this was a 10-ton unit, you got 5 and 5, you got 5, and then this you only need 6. You bring this one back up to 1, as opposed to having 2 and 2. Split DX, you're familiar with the process, but this is the idea of having the DX in evaporated coil and condenser coil separated. Our challenge here sometimes is that where you're going to get that third-party condensing unit, make sure you have the circuiting right. We have a dual circuit. You don't want mixed circuits. We don't have a source specifically for that outdoor compressor or outdoor condenser, so sometimes you put it back on the contractor to say, okay, you're welcome to use it, train carry or whoever you want to get, but let's make sure we're on the same page in terms of what you need. And then Green Neck has developed a remote condenser too for some applications, but I don't see a lot of the split DX, but it is possible. Chilled water, excuse me, you're not gonna probably add a chiller in cooling towers and things, but if it's there and you say, hey, we already got chilled water, we might be picking a unit for somebody to have a chilled water for it.
Probably depends on the size too.
Yeah, exactly. The evaporative coil I mentioned a little bit earlier. Generally, in the western United States, we're dripping water across the pad, bringing warm, dry air, absorbing the energy from the water. That colder and humid air is being discharged into this. Pretty inexpensive at entry level, cost wise, but I even begin to wonder out what, with the water concerns out west. I'm sure I would go this route. It's like you're just throwing water out. We'll get enough for the community to live, but cool.
So you can look at the lake and see what it's done.
Yeah, right. Lake Powell
Yeah.
and
Wheels for boats.
dedicated outside air unit. So we talked about this as a point. So we've seen a big influx of this. And if I had to summarize in terms of a technology, it's decoupling the load on the space. So if we look at the outside air coming into a building, we need to dehumidify. And then you have the space that needs cooling. So historically, if you brought all that air and you're dehumidifying and you're doing the sensible cooling in the unit. Well, the DOAS units, dedicated outdoor air supply, says, hey, just worry about the ventilation that we need, dehumidify that air, and then in the space, have devices that can sensibly cool. So now in the space, you're bringing these two air streams together. So you might have different fan coil units. Okay. So in terms of, let's compare dedicated outdoor air versus makeup air. In a dedicated outdoor air, fully dehumidified, 55 degrees. In a makeup air, we might just temper that air. So you think of a kitchen, you're like, I don't know if I want to bring in 90 degrees, but I don't need to fully dehumidify it. Why don't we just add a little bit of cooling and get it down to 7? So that's just makeup air. We're not trying to fully condition the air to the space. There are times when you need to dehumidify, but you don't want to discharge that cool, damp air off the coil to the space. So you're going to have modulating hot gas reheat to bring it back up to maybe a neutral condition, 68, 70 degrees. Makeup air, we're really not concerned about the reheat. It is what it is, and you just continue. 2-inch injected foam to improve the thermal resistance of the cabinet. 1-inch fiberglass. Again, neutral air. We're not adding that much energy to do cooling, so we don't have to worry as much about that. So we bring that down. Energy recovery is common. This is outside air coming in because we're taking air out. We've already heated and cooled that air from the space. We put an energy recovery wheel. Now we can further reduce that load from the outside air just by recovering that energy. Normally do an energy wheel. We could also do an energy core. And most of the time those are total energy, so it's enthalpy core, so sensible handling. Yes.
DOAS, what does S stand for?
Supply.
Oh,
Dedicated
supply.
outdoor air supply. We still, and I'm not sure I even agree with this statement anymore. How's forward curve, just from what we talked about already. I think we've seen more movement to that mixed flow wheel. Backward incline plenum fans, we've seen more movement of these, even away from those into the mixed flow wheel because of efficiency. Indirect gas heating, most common because again, we don't want our dedicated outdoor air coming in with direct gas and products of combustion. So we use indirect gas, makeup air, not so big of a deal, direct gas.
Could it be heat pump also?
There is an option to do like an air source heat pump. Or if you had another water source.
Or water source, you got a
We have
geothermal.
geothermal in my school. We have all of our dedicated outside air
Yeah.
on geothermal, and we use the geothermal coil as a pre-chip, like the 50-degree loop tap to get it cooled down before it gets to the
That's what Brian's.
Which school system is that?
South Range local schools in Greenfield.
Oh, okay. Okay, occupancy, ventilation, because of the occupancy and the humidity control versus replacing the exhaustive process. We kind of touched on that. So this is how the system would look in terms of a configuration. And we're focusing on dedicated outdoor air as an occupant comfort and ventilation. So here's our dedicated outdoor air unit with energy recovery, bringing in our outside air. So maybe we're taking exhaust air from the restroom and the other exhaust air out of the classroom, bringing it through the energy recovery wheel, tempering that outside air so we don't have to heat and cool it quite as much. So this would be a cooling coil, heating coil, supply fan, and you're ducting that to the classrooms. Well, in the space, you might have a sensible unit just to do your space load. So that could be a small air handler with the cooling coil. It could be with the heating coil. Also, it could be a we have a sensible fan thermal box that has a sensible coil on it. So it could be ducted that way. There's a variety of ways to accomplish this, but it's just to show you the idea.
So with that energy wheel, we are putting some of the restroom exhaust air back into the classroom.
In a wheel, at most, you might have 1 to 3, 3%. ASHRAE, like in other codes, allow up to 5%. So the air that you're taking from a space is different classes. So that'd be considered, I think it's class 2, like above class 3 and 4, you don't want to recirculate, and that cross leakage is not acceptable. So we won't take that in. But like restroom exhaust, anywhere you think about your normal breathing, not that big a deal, like if a little bit leaks over.
Well, like at the Wuhan lab, probably.
I don't think I'd use the wheel in that case. If somebody wanted less, we could do some cores in there instead of the wheel. But like in terms of the wheel and the seals, we've seen as low as 1%, but we allow like that 3 to 5 in terms of a discussion point, and it hasn't been a problem. Some people will add a purge section, which takes part of that outside air and turns it back to purge the wheel before it rotates from exhaust into the supply. If they're concerned about it, that's an option. Generally, not a big deal, but we have ways to address it if somebody is concerned. In terms of this goes back to makeup air, we already talked about it. Kitchens, manufacturing, paint booths, warehouses, ventilating for a process. So DOAS for occupancy, makeup air for process. DOAS units require outside air to be dehumidified. We talked about that, taking it all the way down. 55 degree results in 50% relative humidity at 75 degrees when we reheat. So that's pretty conducive to an occupant comfort. And modulate gas reheat, prevent overcooling, air supply to the space. Talked about that. Makeup air applications do not require dehumidification. Again, something that's room neutral, just to give a tempering to that altitude instead of bringing in 95-degree air. In terms of kitchen hood, we try to show that because this makeup air is replacing what's being exhausted, there's no need to discharge it into the space, just keeping the air near the hood and let it be pulled right out. So many times we'll have perimeter supply plenums around the hood. So if this is a hood, this is a perimeter supply plenum. This is from your makeup air, discharging air around the hood, just being exhausted out. If there are some high-end restaurants who wanted to have, like the chef say, I want my kitchen to be fully dehumidified, fully cooled, and we're conditioning, then you're probably going to bring that air further away, let it come in through the space, pick up every heat load, and then it's exhausted. But I don't see those very often. This goes through the capacity difference in terms of cooling to 65 versus 55 in a minute. So if we look at the difference in enthalpy, in this particular case, we're talking about 8.5 pound BT per pound, and which results in just over 15 tons. If we go now to that 55 degree, we go to 15.5 in terms of enthalpy difference, and now we're up to 30 tons.
So that's with the DOAS unit, not a makeup air.
That's correct.
Makeup air would be even higher because you don't have the energy recovery.
Makeup air, yes, right. So this would, whatever gets us to these conditions, whether it be with or without a wheel, it's just to show the difference in capacity of taking it to 55. So like if this is entering without a wheel, if we were able to use the energy wheel, we could get this down into maybe the low 80s, maybe even like 79. So we've reduced that load, so this number would become less to go from it to 55 still. So that's even an additional way to do it. We already talked about there, insulation, energy recovery. We want to definitely use energy recovery whenever we can. We've talked about class 2, 62 allows any, as long as the project does not exceed 10, typically we're 3 to 5, so we went a little bit louder, or a little bit, you're allowed a little bit more than we even achieve, so we're below the threshold. There's a class 3 and 4 areas where you would not recirculate.
In plain English, what's class 2 here?
Fart. Yeah, I would, simplest way to say it is anything that you would normally breathe
Oh,
in a space. So if you feel the space is fine, then it'd be class 2. Each of us started smoking cigars or cigarettes and stuff and be like, I'm not so sure I was, breathe this constantly, then that would not be class 2.
okay.
Okay, so as you get into class 3 or 4, class 3 is a little more stringent in terms of
Oh, okay.
manufacturing, maybe oil mists, things of this nature. Now you get, you don't want to grease going through a wheel is not good. So it's going to accumulate in the wheel, make it ineffective. Paint booths, paint particles, chemical storage. You might have a nasty chemical or a virus you don't want to research.
Like class 10.
So backward inclined plenum fans commonly used because of the cooling coil or the reheat coil. The cabinets are usually a bit bigger, and we have deeper roll coils, reheat coils that are not typically used to make up air. So that modulated half gas reheat coils not in makeup air. Energy recovery is usually not in makeup air. Most of these things we already talked about. We're ducting. Remember, I talked about had that 3-way discharge on the makeup air for your warehouse just comes in, short duct runs, just putting air in the building. You get to the DOAS unit, you're talking about ducting to each room. So now you have more static. So there's a reference here to multi-room application with longer duct runs. We need to accommodate for that static. So many times the engineers are reporting that. And then the mixed flow wheels and then large open spaces, limited duct. In terms of the controls, any question on anything up to this point before I get into the controls? Everybody's good. We talked about, so I think I'm approaching 2 minutes, so we'll try and do this one. We'll be done by 7. Types of, we're going to cover types of system, enable, and exhaust fan, interlock, heating, cooling, and then supply fan control. This is an example of a controller that you see on many units. So if we look at electromechanical control, EMC, individual control devices, they typically require manual adjustment and there's no ability to communicate with protocols. The other system will be direct digital controls, the DDC system. That central controller you saw a minute ago is usually in the unit. We like to provide that with the unit as a screen for the interfacing with the facilities people. You can program it to do different things, so it gives you more capabilities. And you can communicate via BACnet or any other automation system. So in terms of those EMC system, you're going to open a cabinet, you're going to see a dial for the outside air thermostat. Okay, where you want that set? You're going to have heating temperature control is going to be wired to that max control system. You're going to have terminal strip interface. So you're going to start landing wires on a terminal strip to operate the fan, not operate the fan. Engage heat, disengage heat. You're going to have a remote panel. So mechanical devices, things are going to require you to do something. Are we going to be in heating mode or no heat mode? Are we off or on? Are we going to measure building pressure with the potentiometer? Things are going to be tied back to a panel, and you're going to get a little bit of feedback of there's a dirty filter. This will light up again based on a pressure switch somewhere else, but it's not as automated or as I guess it's called grainy as a controller would be. So this is programmed with a number of different scenarios that can just simply be turned on and off in the field. Usually somebody will tell us up front what it was, so it's programmed, but maybe there's a change. And somebody says, oh, I don't want to do a time clock now. I want to do it on a temperature. So we can easily change that.
So instead of the thermostats, you got all thermistors going back with AC control. Doing pretty much the same thing.
Yep. Achieved at the end of the day, the same thing, just a little different method of doing it. This diagram you're probably familiar with in terms of we're gonna have inputs to the controller, temperature, humidity, pressure, what's happening. It's gonna process, make an output. It's gonna tell something to either start, stop, turn on heating, turn on cooling, fan speed, adjust dampers. Programming is what drives all those decisions, and those will be done in the factory, and then maybe a little field follow-up if necessary.
Time delays.
Yeah, exactly. Time clock, time delay. Again, you're gonna get a keypad or touch screen to see what you're doing. We have a device that allows you, if this was up on the roof and somebody says, well, I don't really want to go up on the roof every time. You can run it back to a remote panel that actually duplicates what's at the unit. Okay? So now you can just go in the mechanical room or the first floor hall closet and do anything you need to the unit from down there as opposed to going to the roof. And then the other option is there's also a onboard graphical user interface that if you had an internet connection, you can actually dial into the unit and a little nice visual comes up that you can make adjustments that way.
And special software for that.
Nope.
Available.
Nope, it's just a website address. You type in,
It's like your home
190.
thermostats and stuff like that.
pardon me?
It's like your home thermostats and
Yeah,
stuff.
you could call up on your phone, make a change at home, same type of thing. People just log on with the laptop or iPad and come up and then you make changes. It's password protected, it's not. But we show a demonstration sometimes where we'll pull it up the unit agreement, show you what's happening somewhere. Adjust that. In terms of the unit mounted control, this is the idea that not all controls are created equally. Some don't give you the visual feedback or the menu driven screens versus using lights. You have 2 red lights, 1 green light, yellow. It's a little more.
The ones that just have the blinking lights, are those codes all notated inside the door of those units?
We do not use this. For that very reason, we use it. But this is an example of what you need to. We try to remind people you need to specify what you want. As far as you can't just.
If it's spec'd out, it bumps those other people out.
Right, or makes them at least come up to this level and don't undercut.
Right.
Into something like this. So standalone without communication, if maybe you didn't have the automation system, well, this would allow you to operate that. Easier startup and troubleshooting. I mentioned about the ability to change it in the field. Okay, so you bring your makeup air because you have a fast system of exhaust. So normally you're interlocking areas. So the exhaust fans come on and sucking air out of the building. Let's turn on the makeup air. So those are interlocked. And makeup air enabled first when it proves the exhaust fan is enabled. So it just kind of depends on the application. So for code, if the exhaust fan's on, you got to bring. If the code says also if you have a fire, you shut the makeup air off and you make sure the exhaust fan's on. So there's just interlocks that are required depending on the application. I just mentioned a disabled in a fire and so International Mechanical Code talks about if they sense heat, the exhaust fan needs to come on. If you're cooking, the exhaust fan needs to come on. There has to be an interlock between those two. But at the same point, well, if you're going to start sucking air out of the building, bring on the makeup air. So we'll interlock those two. NFPA, I just mentioned about the exhaust fan coming on, the makeup air shutting off. Kitchen ventilation, we see a lot more requests for variable volume kitchens. So you think of a kitchen with a big battery, maybe a hospital, maybe a high-end restaurant with a big cooking mode. Trying to think, maybe a food court. Yeah, you could probably do a food court too. But areas where you might have a big load in the morning and then a lull, and then a big load at lunch, and then a lull till you come to dinner, and now you have another big load. Well, you don't want somebody coming on and turning on everything 100% all the time. They're not cooking all the time. So we have systems in place that will have a variable volume and says, okay, wait a minute. If they're not cooking and we don't sense this X degrees of heat, turn down that exhaust, turn down the makeup air, and those two will just track. Okay, you always want a kitchen a little bit negative. So if you're exhausting 5,000 CFM, maybe you're only supplying 80% of that. Okay, and so as the exhaust comes down, supply air comes down. So you're saving energy both ways, variable volume. Garage applications. Obviously, local codes. In a garage, there's usually a constant ventilation component that you need to be watchful for, and then you're monitoring for carbon monoxide and nitrogen dioxide. So mostly diesel cars and diesel, we kind of have dual sensors usually that are going to sense for both. So that system's monitoring, say, we have an elevated level, kick on the exhaust fan. Maybe you have an exhaust fan that's running at 50%, and it set makes the detection, ramp it up to 100%. And with the advent of like EC motors, you could send that EC motor 10 volts, 100%. Send it 5 volts, 50%. 2 volts, 20%. Below 2 be off. Zoom 2 is on. Sound an alarm if for some reason you got above an unacceptable level. I talked about interlocking. Okay, this one, makeup air supplying high amounts of oxygen. Never enable, disable heating or cooling based on room temperature. Okay, that would be a case where suppose it was 0 degrees outside and your space was 7 degrees. And you said, oh, let's enable or disable the heat because we're satisfied. Well, now you're bringing in 0 degree air. So what you want to do is monitor the outside air temperature coming into the unit. So you say, okay, if it's 0, I'm going to heat that air at least to a neutral condition, whatever that neutral condition is. So makeup air should be based on the outside air temperature, not the space temperature. Discharge control, because we want to maintain that neutral condition. So if it's 60 degrees, 65, 70, whatever it be, but you want that burner, indirect or direct firing to create that leaving air temperature. We talked about Maxtrol and the option to revolver ride. There's a different series, 14 or 44, depending on how it's configured, or external control. DDC controls, we talked about those. Sometimes you're unique to manufacturers, but if somebody has a real good controller, we find multiple people will buy that controller just because it's good, it's durable, and it gives them easy of interfacing. Fan speed control. Again, variable volume kitchens, whether sending 0 to 10 volts or building pressure is really common. So if they begin to notice, hey, the building's going negative, let's kick on the supply fan and bring that up until we maintain maybe 0.01 differential, 0.02, whatever it be, without allowing it to go too negative. And usually doing that with like magnet helix gauges, referencing the outside to the inside. So it's sensitive, great differential support and on the supply fan.
Earlier, you mentioned you always keep a kitchen slightly negative. Because of this ability, why is that?
Just to keep any odors into the kitchen as opposed to going somewhere out. So if it would start to go pot, if this was a kitchen and we oversupplied, we'd have those cooking odors going out into the hallway, into the restaurant.
Exhausted into the bar area to get them to buy more food. Like the old popcorn machine at the movie.
Oh, yeah.
Exhausted into the-
Smells good, right? Yeah,
So it depends on what they're cooking.
Minimum fan speed, so if we have, okay, I think we had an example here that would be, yes. So when I talked about earlier, that minimum fan speed, you have to watch how much the fan can do from where it's operating. So if we had a 1725 motor and it was operating at 1200 RPM, and we said we're going to allow the VFD to take it down 30%. We took 30% of that full speed, we'd be at 518. And we remember our fan laws in relationship with RPM and CFM being linear proportional. That gets you down to 43%. So based on the VFD, taking this motor, lowest we could go is 43% of our CFM. Of our max. So we can't go to that 30% that I mentioned earlier. This particular case, we go to 43%. The next example, if we were overspeeding the motor, which is feasible and possible, just go over 60 hertz, or a 2000 RPM fan, we do that same math again, we can go down to 26% of where we were at. So we look at each case, our software will produce your minimum that you're allowed based on the selection, and we just remind people, say, okay, you picked a unit for 10,000, this right, we can go as low as this. Sometimes it varies between 50% to 30%. So this is trying to show us that we have to watch it. There's no like steadfast rule. 50% would probably be like your.
So you've got to up the horsepower a little bit to be able to overspeed it to hit your max airflow, but that'll allow you to get down to the lower than.
Yes. We watch that. On the cooling side, you're familiar what happens with low airflow cooling from some coils of oil, like you mentioned earlier, Terry, about oil. Low heating, the cycling, the high limit trips, overheating. We don't want the condition where the heat exchangers burn in there and there's no airflow over. And then rule of thumb, that 50% that I kind of reference kind of keeps you safe, but you could go low. Okay, so in summary, we talked about fans, we talked about heating technologies, cooling technologies, and controls. Did it pretty fast. I am 10 minutes late, so I apologize for that. Any questions?
Everybody does it different.
In terms of
Every manufacturer.
Looks like there's an option for basically any setup you got.
Yeah, basically, I think we've been pretty fortunate in that regard to satisfy most requests. Sometimes you get special construction, somebody wants stainless steel or wash down units. That's not,
Depending on the fumes they're dealing with, I've seen that.
yeah, or like medical facilities, they want to wash them down.
Sulfuric acid.
That, we get into some of those, but for the most part, the purpose of tonight, general makeup air for 90% of your applications, yeah, there's an option for it, but. And it's, it's not only Green Egg or us, it's others too.
You have any credit? Oh,
Years ago at SK Loman, they had all kinds of exhaust because they were grinding off copper and graphite and all this other stuff. So they had two huge blowers with natural gas coming in. So when they had the gas shortage in 75 or whatever, they shut both of those off. So they still had to have the exhaust for all the grinding. So you couldn't, a girl couldn't pull the door open. She had to wait for King Kong to pull the door open.
Something like that.
Everything came in around the doors and windows. People were freezing.
Well, that's because all the unit heaters are off, because they're all tripped off on school switches.
Well, when they said when we had X amount of natural gas, they shut us down and sent everybody home. You only get this much gas and that's it. Shut down, we turn off your gas meter and you go home.
Yeah, thank you for sharing that, Phil. Yes, anybody else would like one, nobody else here, feel free to, would you like to? Yeah.
Thank you, Rob.
You're welcome. Thanks for that.
If you're, if you have any questions, anything, and feel free always to reach out to myself or any of us. Does anybody know anybody else in our company, Air Control Products?